right, hi folks, welcome to Math 11. We're headed into section 7.2. Hopefully 7.1 went okay for you. So 7.2, we're gonna start talking about circles. And we're gonna start putting triangles inside circles, and we're gonna do all kinds of things with them. Wicket, down, down, just a second, down. Wicket. Good boy. Okay, sorry. We're going to start putting angles inside circles. So we have to talk a little bit about some terms that they're going to use. So I know I can't draw, and I'm sorry, but let's pretend that's a circle. Any line that goes from one side to the other side of the circle, I don't care where it is. If it goes from one side of the circle to the other side of the circle and it stops, that is called a chord. Now, if you have a chord that goes through the middle of the circle, okay, that is called a diameter. And if you have a line that goes through 2 points on the circle, but it keeps going through the circle and it just keeps going, and it goes through 2 points, that's actually called a secant. And they don't have this in your textbook, but I'm going to teach you anyway. If you have a line that touches the edge of the circle in only one spot, just one spot, that is actually called a tangent line. All right, so they're going to start using those terms a little bit, so you need to know what they mean. Now, they're going to give you some more theorems here, but don't worry, we're not going to be doing, you are not going to be doing, I'm going to be doing a few, but you're not going to be doing, whoops, any more proofs. Just a second, I scared my dog. Down, back down, wicket, wicket, down, down. All right, so then they give a theorem, and they talk about a perpendicular bisector. So let's talk about what those fancy words mean. Perpendicular bisector. If you have a chord, and it just goes from one side of the circle to the other, and you draw a line in the very center of that chord, and you draw it up through the circle, somewhere along that line is going to be, that's probably not it, somewhere along that line is going to be the center of the circle. If this line, and this line can keep on going if it wants, if that line is perpendicular to the chord and it goes through the center, then this line is called a perpendicular bisector. All right, so then they have some theorems, and they say one of the theorems about the perpendicular bisector, so it's called chord perpendicular bisector theorem. And it's on page 398. It's summarized for you on page 398. And one of the things that they say, there's 4 different things that they say about a perpendicular bisector. There are 4. The 4th one is kind of dumb. It's sort of obvious. But the other 3, so the first one is that the perpendicular bisector of a chord has to contain the center of a circle. The perpendicular bisector of a chord must contain the center of the circle. So if this really is a perpendicular bisector, the center will be on that line somewhere. If it was over here, it wouldn't be a perpendicular bisector. It might be perpendicular, but it wouldn't be a bisector because it wouldn't be cutting the line in half. The second thing that they say is that the perpendicular bisector of, I'm not going to write this all out, it's on page 398. This is number 1. Number 2 says if you have 2 chords, okay, I'm going to shorten it. If you have 2 chords, the perpendicular bisectors cross at the center of the circle. Let me tell you what that means. Let me show you what that means. So if I've got a chord there, and let's say I have another chord here, and I draw a perpendicular bisector to that chord, the place where they cross is the center of the circle. And finally, well, not finally, the third one, the perpendicular from the center of a circle to a chord bisects the chord. In other words, if I have a circle and I draw a chord and I know that the center is here, if I draw a perpendicular line from the center to that chord, it automatically is bisecting it. It automatically is cutting that chord in half. Now, obviously on my drawing it's not. I don't think that was completely perpendicular. I think that probably is more perpendicular. I don't know. But it would automatically cut that chord in half. So if you know where the center is and you have a chord, if you can draw an exactly perpendicular line, it automatically cuts that chord in half. The last one says the line segment joining the center of a circle and the midpoint of a chord is perpendicular. In other words, if I have the center and I draw a line and I cut this one in half, then it's automatically perpendicular. It's just sort of the opposite of what I just said. So they do some proofs on that. They do some proofs for that. We're not going to bother to do the proofs because it just doesn't matter, because we're going to actually start putting numbers into things. Yay! We're going to start putting numbers into things. So the only example we're really going to look at in this section is example number 3 on page 398. You need to know those theorems, not so that you can write them out for me. I'm never going to say, please write the theorems of the perpendicular bisector theorem. I'm never going to say write that. But you do have to know them so that you can use them. So in example 3, it says you have a hemispherical pot. So a pot that is a half of a circle. And it's for a hanging basket. You're going to put soil in it, and then you're going to plant flowers, and the flowers are going to be all pretty, and spring is finally going to be here, and that would be great as it's snowing on the day I'm recording this. It says the width of the surface of the soil is 30 centimeters. Now, you are not filling the pot to the top with soil. You need to be able to plant the plants down inside. So you're really only putting the soil maybe up to about there in the pot. And all the way across there is 30 centimeters, okay? So from one side of the pot to the other. The question is, the maximum depth of the soil is 10 centimeters. So from here to here is 10 centimeters. And it says find the radius of the pot. So in other words, if this was really half a circle, from the center to the edge of the pot, how far is that? Now, a radius can be drawn anywhere. It can be drawn from the center straight to here, but it could be anywhere. My radius could also be from the center straight down to here. It also could be from the center straight out to here. all of those lines should be the same length because they are all a radii of the circle. So I'm going to start putting some numbers into here, all right? The maximum depth is happening exactly halfway through because it's a circular pot, which means that from here out to here would be 15 centimeters. I know that. Now what I'm going to do is I'm going to say that the radius is x. And it doesn't matter, again, that this is a radius, so it's x. This is a radius, so it's x. But this is also x because it's also a radius. So notice right here, let me just use a different color. Notice right here, I actually have a little right angle triangle. And what I want to know is I want to know the hypotenuse of that right angle triangle. So I know that x squared is equal to 15 squared plus whatever this side is. So what I have to do is figure out what that side is. So if this is 10 and the whole thing is x, right? So the whole length is x and that piece is 10, right? And so 10 plus whatever that red piece is will equal x. Well, let me just rearrange this. If I move this over here, I have x minus 10 is equal to whatever that little piece is. So this I could label x minus 10. Hopefully you can see that. So the other side of this little right angle triangle is x minus 10. So I have the hypotenuse, which is x squared, is equal to 15 squared plus x minus 10 squared. So now I have x squared is equal to 15, not 115, is equal to 15 squared plus, now don't just tell me that that is x squared plus 100. If it's x minus 10 squared, you have to do FOIL. So this is going to be x squared minus 20x plus 100. So this is going to be x squared is equal to 15 squared, which is 225, plus x squared minus 20x plus 100. So if I move this x squared over here, that's nothing. 225 plus 100 is 325 minus 20x. So if I move this over here, I have 20x is equal to 325. And so x is equal to whatever 325 divided by 20 is. It's 16.25. That is what x, or the radius, is, which is what they wanted to know. So again, I used my knowledge of the Pythagorean theorem and just really some logical reasoning to figure that out. I'm going to get you to do a few questions on page 400. They'll be listed on the assignment. There's not really a whole lot of work to show. You have to use your knowledge of perpendicular bisectors. Hopefully you understood the lesson. You'll have to use that to figure out the missing things that they want to know there. So I'm going to post that with this lesson, and you can do that, and we're finally getting into numbers again, which is great. All right, we'll talk to you again soon. Bye.